All right, today we're going to discuss something called Amdahl's Law, and it has to do with you trying to speed up your program by throwing more cores at it. And this is really important. This is a fundamental law of parallel programming, and it really shows up in a big way in multi-core programming. And I've heard from other students that this is a common interview question. So explain Amdahl's law. So yes, this is a good thing to know. Plus, we'll use it in the programming assignments. All right. Amdahl is a person named Gene Amdahl, who was one of the big people in mainframe computing. And mainframe computing had multiple processors in it. So, now we put multi-cores in a chip this big, and at the time it was multi-processing, but the idea still holds. Okay, let's define speed up. Speed up is, and there's two ways to compute it, and we'll give you the same answer, the time it takes to run it with one thread divided by the time with n threads. Okay? In theory, one thread takes longer, so this is a big number over a smaller number, and you get a speed up greater than 1. Or if you've computed performance, so many somethings per second, well, then you take the performance with n cores divided by the performance with 1. Again, the numerator should be a bigger number than the denominator, and we'll get a speed up greater than 1. Okay, so these give you the exact same number. Okay, and then speed up efficiency is the speed up you get when you go from 1 to n cores divided by the n. And so we would love it if we can get 100% efficiency, right? 100% efficiency would mean with 4 cores, we get a speed up of 4. And that would be great. Well, your experience with perpetual motion machines is probably telling you that's not going to happen. And you would be right. But let's talk about why. Okay, so multi-core is not a free lunch. We don't get 100% speed up efficiency. Okay, and the reason is in any program, a certain percentage of that program, a certain slice of that, is able to be parallelized, and a certain slice is not. This is known as the scalar slice. The scalar slice cannot be parallelized, but the parallel slice can. Okay, so that gives us a speed up of, well, this 1 over. Now we take the fraction that's parallelizable and we divide by the number of cores. Now, if it's parallelizable, then having 2 cores will make it run twice as fast. But we added the F sequential, which cannot be sped up by increasing the number of cores. Okay, and because these two fractions add up to 1, you can also express it like this. F parallel, the fraction that's parallelizable, this looks like about 2/3 here, divided by n plus the sequential part. And so here's what's going on. If this is the sequential part and this is the parallel part, with 1 core, okay, here's the execution time. And what's in the sequential part? Well, you got to get the program started. You've got to set up some local variables on the stack. You've got to maybe read in data. But when you're down to the computing, yeah, that can be parallelized, but that other stuff can't. Okay, so if we go to 2 cores, that means that this can be divided in half and each run simultaneously on another core, on 2 cores. And so that means in execution time, here is how much the parallel part of your program takes to run, but the sequential hasn't changed because it can't. Now you go to 4 cores. Here's the execution time for the parallel portion, but the sequential can't be sped up. Okay, you add infinite cores. This will eventually go to 0, which of course it won't. But you're still stuck with this. The sequential portion doesn't get smaller. and it doesn't go away. It just becomes much more dominant. And if you take Amdahl's law and you start plotting it, so the x-axis here is the number of cores. Here is the speed up you get. If my program has 90% parallel, that's the parallel fraction, 90% of what the program's up to can be parallelized, here's the speed up you get. And yeah, okay, with 15 cores, I'm only getting a 6x speed up. And notice this curve starts to flatten out. And eventually it will pretty much flatten out. So 30 cores, I'm still only getting 7.5. Okay, and this is part of the reality. And 90% is a great parallel fraction. 90% is just a really good number. What if you're down here at 20%? Well, this flattens out right away. Notice if you throw 30 cores at this, it makes no more difference than if you had thrown 2 or 3 at it. Okay, it tops out. And really that's what Amdahl's law is telling you, is no matter how many cores you throw, it's going to top out somewhere. And even the 90% curve will flatten out. So 40 or 60, 80. So what this is telling you is if your company comes to you and says, hey, we want to spend $1 million adding 100 more cores to your desktop machine. Oh, how cool would that be? This is the kind of thing you ought to look at. What is your parallel fraction? That tells you how much you can actually get from those 100 cores, which is probably not going to be worth $1 million. If you graph parallel fraction on the x-axis and then do speed up here, basically you're inverting. This graph is, you can see that as you add more and more cores, well, for 2, this just doesn't go up much, even with a 90% parallel fraction. Yeah, if you got a bunch, like 10 cores, yeah, that goes up. But again, it's not 10. With 10 cores and a parallel fraction of 90%, which is great, you get a speed up of about 5.5. Okay, and we can do this with speed up efficiency as well. And so as you add more processors, in the same way that this graph flattens out, so does speed up efficiency. Speed up efficiency drops because the addition of one more core doesn't really make one more core worth of advantage. Okay, that Amdahl's law curve is flattening out. Again, this is just the reality. This is a little bit of a dismal story because you can't simply throw more cores at things and expect to double your performance with twice as many cores, but it is reality. Yeah, we can invert this graph as well. Okay, but obviously there's an advantage if you know your parallel fraction. How can we get that? Well, this is Amdahl's law. And so now if we go, well, algebra, 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 some more algebra, algebra, some more algebra, algebra, we get this, is if you have run an experiment with speed up, so maybe you ran your code with 1 core, then you ran your code with 8 cores. Okay, n would be 8. It's always 1 to something. Okay, it's never like 2 to 4. It's 1 to something. So n would be 8 divided by 7 times the speed up minus 1 over the speed up. That's just what you get from the algebra. Okay, this is how you can compute your parallel fraction. And we ask you to do this in some of the assignments. Okay, so probably you want to take your maximum number of cores that your system has and use that to speed up. So you've got a time it took to run with 1 thread, a time it took to run with 8 threads. That gives you the 8 thread speed up plug into here, that gives you the parallel fraction. And the significance of knowing that is you can generate graphs like the one we just saw. You can also compute the maximum speed up you will ever get. Knowing that that sequential portion is the bottleneck, you throw 100 cores at it, the parallel stuff just runs in almost zero time, but the sequential runs in the same amount of time. So if we say, what's the limit of Amdahl's law as the number of cores goes to infinity? Well, the F parallel goes away, and we're left with just F sequential in the denominator, which is 1 minus or 1 over 1 minus F parallel. And so if, let's say we're doing this 0.9, the maximum speed up is 1 over 0.1, which is 10. So even if you threw 1,000,000 cores at it, you would never go any faster than 10x. Okay? And again, this helps you decide things like, oh, how much money should we spend to get more cores? Well, given the parallel fraction that this piece of code has, we are going to only get a factor of 5 no matter what we do. Okay, this is because those curves flatten out. Okay, so this is good to know. Now, before this all sounds too dismal and you run out and drop the course, there is something called the Gustafson observation. And this was in a paper. What Gustafson observed was the reason people buy more cores is usually not because they're trying to speed up their existing code. It's because they're trying to run bigger problems. Okay, they want to increase the number of numbers they add up to a gazillion instead of only a billion. Or they want to break up their finite element mesh into smaller elements and solve that. Okay, now that plays perfectly into Amdahl's law, because if you've got, say, double the data, that's going to increase your parallel fraction. Okay, we're assuming that the sequential part is still going to be roughly the same, but the parallel fraction will increase because that's the bigger data set is the part that can be parallelized. So I was playing with this one day and I said, okay, let P be our amount of time spent doing parallel, and S is the sequential. And so the F parallel is the amount of time you do parallel plus the sum of the two. Okay, which means the serial part of it is going to be this. We're just solving that using algebra. And we're just going to set P equals 1. We're just going to scale the whole thing. So the parallel part takes 1 second. Okay, so now S is a fraction of the parallel part. And if we now say, well, let's scale up the parallel part by a factor of n. Let's have n times more data. Well, that means the new parallel fraction would be this, which means if we multiply the amount of time you're doing parallel by capital N, we get this. And eventually we get this for a new parallel fraction. Okay, so if we graph it, we get this. So here's the original parallel fraction. Let's say we're kind of abysmal here at 0.4, but if I do 2 times the amount of data, that would raise my parallel fraction to 0.57. If I do 10 times the amount of data, that would raise my parallel fraction to 0.87. And so people have described Amdahl's law as kind of dismal and discouraging, but then they've described Gustafson's observation as sort of the cheery part. The sun coming out behind the cloud is, if you really are buying more cores in order to address bigger data sets, you will end up with a bigger parallel fraction, which means you will end up with a bigger maximum speed up. Now, we can play all the graphing games, 10 times as much data, and we're a parallel fraction of 0.4, that parallel fraction comes up to here. And notice these curves start to level out as well, which makes sense, okay? If I have 100 times more data, there's going to be a limit to what I can accomplish if I started out with a parallel fraction of 0.4. Now, one of the tricks to this, of course, is that you try very hard to squeeze down the sequential portion of your code and increase the parallel part of your code so that your parallel fraction starts out with a bigger number. Yeah. Anyway, this is Amdahl's law. Pay attention to it. I hear that it's asked a lot in interview questions.